Shown here is an op-amp-based square wave oscillator, also known as a stable circuit, because it has an output oscillation like this. It's not stable. It just goes from most negative voltage, negative VD, because that's our negative supply, and goes to most positive voltage plus VD. That's our positive supply voltage. So this is the situation with the Vout. We are using a combination of positive feedback in this circuit. As you can see, this connection going to positive input terminal, and negative feedback in this circuit, this connection going to negative input terminal. So combination of these positive and negative feedbacks generate this astable behavior. Now, when the voltage at the output is at negative VD, then there is a voltage division between R2 R1 because we are assuming ideal op-amp, so input impedance is infinite, and then no current is going through this connection. Therefore, whatever current coming from the Vout goes through R2 and R1 in series, therefore creates a voltage division. So therefore, when we are here in this range, so I'm talking about output being equal to negative VD, then the situation for V plus, which is the voltage at the positive terminal, is like this. V plus looks like a negative voltage, of course, and the value of that negative voltage during this time, so x-axis is time, by the way, so just to be clear, we are talking about x-axis time, and when we are in this range of time, output is at negative VD, V plus is at, as I said, a voltage division between these two guys, so it would be R1 divided by R1 plus R2 times negative VD, which is the Vout. So negative R1 divided by R1 plus R2 times VD. So at this voltage VR, now when we are in this range, assuming that initially this voltage is at this negative terminal value voltage at some voltage, then it has to reduce, and because there is a current that is flowing through this capacitor from 0 voltage toward the negative voltage at the output, so going to output. So given that, the value of voltage here start going down and drop up to the point that it hits the lowest level that it has to, which is matching V plus. So it will keep going down up to the point that it reaches the value of V plus at this level. As soon as the negative voltage, so let me just make sure there is no confusion about what I wrote here. So the direction of this arrow is just saying the current going to V out. It doesn't have anything to do with negative. So the V negative here is showing a voltage drop that goes down. It's showing a voltage drop that goes down up to the point that it reaches the value of V plus equal to this. When it gets to that value, then the voltage at negative and positive terminals are the same. In that moment, then right after this moment, when V negative becomes even less than this value, then the positive terminal would be having higher voltage, and then the negative terminal resulting V out jumping up. So that's exactly this moment when V out jumps up from the negative VD to plus VD. And as soon as that happens, obviously because V out to V plus is just a voltage division, the V plus also jumps to a positive voltage now. And that positive voltage now is just again, because of the symmetry of the supply voltages we have here, that positive voltage then becomes V plus equal to the exactly positive value of this value shown here. So plus R1 divided by R1 plus R2 times VD. So that's the value of positive voltage here. Okay, in that time, this negative voltage, we agreed and we discussed that it got to exactly negative R1 over R1 plus R2 times VD. And then it now has to catch up from this point on, and has to catch up and get to the value of new positive the value of voltage, the new voltage of the positive terminal, which is this value. The moment it hits that, then right after that, because the voltage of the negative terminal reaches to the positive and gets above positive, then it means the negative terminal beyond that point would have higher voltage than positive terminal, would force the output of op amp to just go to the lowest voltage, which is the negative VD, and that's why we get back to negative VD at the output of the op amp. So at this point, the voltage for the negative terminal is now plus R1 divided by R1 plus R2 times VD. All right, so the lesson learned is the negative terminal start doing an exponential sort of oscillation, exponential because it's governed by exponential function. Um, so start doing a oscillation between the negative R1 over R1 plus R2 times VD to plus R1 over R1 plus R2 VT and keeps going on forever. And the positive terminal start oscillating between these two values, And the output voltage oscillate between these two values. So now the question is, now that we know the circuit behavior, can we come up with, let's say, the value of this duty cycle, or let's say so if you refer to this as T1, and if you refer to one period of this guy as, of course, that would be 2 times T1 because of the symmetricity we have here, but it's the period of the rectangular waveform or square wave waveform. So let's compute that. In that case, there are many ways to do this. It is a simple RC circuit here. So from the equation of voltage of capacitor in a simple RC circuit, you know that it's well known that voltage of capacitor, so it's well known that voltage of capacitor at time t is equal to the final voltage of capacitor, so VCF, plus the initial voltage of capacitor, VIF, VCI, initial voltage of cap, minus V cap final times e to the negative t over RC. T is time, RC is the just a constant here, time constant. All right, which in this case would be RFC, of course, because the resistor that is related to C is just RF. So let me just clean this up. So this resistor needs to be clearly written as RF times C. That's our time. That's our constant here, time constant. Now, of course, this is easily obtainable. I mean, if you don't want to write this, the easiest way is just writing one simple KCL here or KVL here. However you want to do it, it would be super easy. So you can say just simply the negative terminal at time t, or you can say VC, is equal to. I mean, you can do it in many ways. If you want to do, for example, say Laplace transform, it would be as easy as saying as this. So you would say V negative in Laplace domain is just a voltage division between this cap and the series of RF and this cap. So it would be V out times impedance of cap, which is 1 over CS, over 1 over CS plus R, F. So then you can just say V out as a function of the negative terminal, and you can play with this thing, you can simplify it. It would become 1 over, so if you want to put it this way, let's keep it as it is. Let's keep it as it is. Okay. So in this scenario, it becomes V minus equal to VOS times, when you shuffle things around here, it just simply becomes 1 over 1 plus RFCS, which is an integrator as we expected. This, when you go out of the domain of, when you transform it back to time domain, 1 over 1 plus RFCS result in e to the negative t over RFC as expected. And the reason intuitively that you can think about this equation being a correct behavior in a simple RC circuit is because at time zero, time zero meaning that the starting of behavior, let's say here, let me highlight it in different color. So at time zero, meaning, let's say at this time, you're starting moving up from negative R1 over R1 plus R2 VD at this point to get to some value. You are charging up, and the voltage at the output is VD, and that is the voltage that we are going toward. So if you would have infinite time, the V negative terminal would reach to VD, matching the output. But in the middle of that process, op-amp changes its behavior, and therefore things start changing. So in that process, you would say at time zero, e to the zero becomes 1, VCF cancel out VCF, so VCI remain, which means VCT is equal to VCI, initial value. At time infinite, e to the negative infinite becomes 0, remove this thing, and therefore VC infinite. So all I'm trying to say is VC at time t equal to infinite, nominally, is VCF, and VC at time 0, reference time, the starting point of process, is just VCI. And you can obtain it by just substituting t with 0 or infinity from this equation, and you can see it would end up with this outcome. All right, so having this in mind, I guess all I meant is this equation that I wrote intuitively, knowing that it's a simple RC circuit, is also quickly obtainable by just transforming this equation in S domain back to time domain. Okay, so let's start from here. When you are at this point, the voltage of cap, as you can see, is, assuming you think of cap like this with this definition of voltage. So that's our VC T. Um, that's our voltage of cap at time t with this sign. And then with that in mind, we can say um, the final voltage during the process that output, say, is in negative value. So we are here. So let's say output is a negative value, and this thing is charging down. So we are going down. So during that process, what's happening is you're saying, or doesn't matter. I mean, I can do the other way. I'm just trying to make it as simple as possible. So imagine we are at the most negative voltage for the cap, and we are charging up to get to the most positive voltage for the cap before the oscillation behavior change again. But we know that if this oscillation behavior wasn't happening, the cap would have charged up to the V out voltage, which is plus VD. So all I'm trying to say is during this charge up process, the VC final would have been VD, and the VC initial obviously is the initial value, which is here. This is VCI. So now substituting for this values, and let me change the color to different color. So substituting for this values, we can see that VCT, so voltage of capacitor as a function of time, is VCF, which is VD, and then plus VCI, which is this value, so negative R1 over R1 plus R2 times VD, and then minus VCF, which is minus VD, times, of course, e to the negative t over tau. And tau is our time constant, which is RFC. So let's refer to this as tau. All right, now let's just do a little quick factor out. So what we can observe is VC at time t is equal to VD times, I just factored out VD, factor out a negative sign because you can see that both of these guys, they have negative, so minus, and then if you do a little simplification, you end up with this outcome. 2R1 plus R2 in the parentheses, and then in the denominator you have the same as what you have here, R1 plus R2, and then you have e to the negative t over tau as expected, and this is the equation that governs the voltage of cap. But we are interested in finding this T1, the charge up process. So from the lowest to highest, so the target voltage at since we started from the value of negative R1 over R1 plus R2 for VD, the final, not the final, the target voltage at the end of this duration T1 that we get to would be the positive. Let me change the color again. Would be this target, right? This target. So we are trying to get to this target, and therefore this value VCT target is R1 over R1 plus R2 times VD. That's the target voltage for voltage of cap, and equal to the rest of the thing that is written, equal to VD times, of course, the rest of it, 1 minus 2R1 plus R2 divided by R1 plus R2 times e to the negative t over tau. Okay, so we do a couple of simplification quickly here, and VD cancel out with this VD, and then if you do multiply both sides by the denominator, which is R1 plus R2, what you get to is this outcome. You would get to R1 is equal to R1 plus R2, and then minus 2 times R1 plus R2 e to the negative t over tau. Again, tau is Rf times c. So obviously R1 cancel out R1 here, and what you finally get to is this outcome. e to the negative t over tau is equal to R2 over 2R1 plus R2. Okay, let's take ln, so natural logarithm of both sides. Let's do that just to get rid of the exponential, so it gets to linear domain here. So so it becomes negative t over tau, get rid of e, is now ln of R2 over R1 plus R2. I can do one simple quick trick, which means, so it is plus R2 here in denominator, and using a simple trick, this can be just written negative ln R1 plus R2 over R2, just swapping numerator and denominator. And now we have a negative sign here, negative sign here. So ultimately what I got to is t, or time, or basically T1, because I calculated the time it takes to go from the negative voltage at negative term at V negative to positive voltage. This red transition that I highlighted. The time it takes to do that red transition, which is effectively T1, is equal to tau ln of R1 over R2 plus, I forgot about a 2 factor here, so that's very important not to forget. Let me make a course correction here. So I'm glad that I caught it. So it's gonna be 2R1 plus R2, and then 2R1. Let me just make sure that it's highlighted clearly here. 2R1. So what we get to is 1 plus, because R2 over R2 is 1, and then 2R1 over R2. Very interesting. This is in second, of course. So what we found is the half period of the oscillation. And of course, the period of oscillation is just 2 times T1. It's a 50% duty cycle square wave oscillator that we have constructed using just single ideal op amp as shown here. I hope that you found and you find this example helpful in understanding how the square wave oscillator as a stable circuit is working, designed with a 1 op amp.